Well, here's Mike Cave. He's going to be talking about Ceph and compute in Canada. So he's also looking at doing a meetup in which area?
Victoria.
Victoria. There we go. So there we go. Take it away.
Good afternoon, everybody. Thanks for sticking around for the last presentation. It's been a long day, so I won't keep you long. I'm just going to talk a little bit about how we use Ceph in Compute Canada. My name's Mike Cave. I'm a senior Unix administrator with the University of Victoria in research computing support. So first of all, what is Compute Canada? Well, it's Canada's national digital computing research platform. We provide researchers with HPC resources, cloud resources, storage, backup. It works on a combined funding model. So we have 4 consortia. I can't get the pointer to work. Whoops. Anyways, you can see there's WestGrid, Compute Ontario, Calcul Quebec, and AceNet. We all work together to provide these resources at 5 major sites across the country, but we're supported by over 70 institutions. So we have members that work on the Compute Canada national platform. They're, the cloud teams, the HPC teams, storage teams. We all work together in order to provide the researchers with the best support we can, as well as evergreen hardware. So by doing a combined funding model, we've got the ability to evergreen our hardware rapidly and keeping everybody up to date. We're also connected by a 100 gigabit coast-to-coast network, which helps for, obviously, data transfer. So currently we have 4 active HPC sites. You can see them up there. The newest one is Beluga. It just came online at 35,000 cores. Next one's in Vancouver at 60,000. We've got Graham at 30, and Niagara at 60,000 as well. On top of this, we have 4 cloud sites. Cedar, East, and Graham are kind of partner clouds to their respective HPC clusters in their area. And then we've got Arbutus, which is a cloud-only site. There's no HPC attached to it. All the sites are general-purpose clouds, web portals, prototyping. The smaller cloud installations, like I said, they're attached to HPC, so what they allow the researchers to do is to display their work that's being generated out of their cluster without having to transfer it necessarily to Arbutus at the outset. So we use Ceph across all of our clouds. We vary in size from 4.5 petabytes of usable storage at Arbutus down to 100 terabytes at East, 700 at Cedar, and 100 at Graham. So, okay, I'm an Arbutus admin. I don't know a lot about the other sites. We work with their teams closely, but I don't actually get my hands into the configurations. We collaborate and we work together to come up with common configuration, and so Arbutus is my baby, I guess. I like hearing that there's lots of people with teams of storage specialists. I am the team of storage specialists. So Arbutus is the largest cloud installation for Compute Canada. On offer, we have 10,000 physical cores. We virtualize them, so we actually offer almost 20,000 cores. 4.5 petabytes of storage usable. On top of prototyping and web portals, we also process data for Atlas Tier 2 and Tier 3. We host training and workshops, and we host virtual clusters. So we engage our communities by allowing them to host their workshops to teach people about HPC, so they can set up a prototype cluster and learn all about Slurm without actually taking time on the major clusters and, having to actually schedule. So what were our first steps? Ceph was initially deployed to support West Cloud Phase 1. Started as 500 gigs of triple replicated storage and deployed CephFS to help with persistent instances. At the time it was deployed, persistent instances couldn't be migrated very easily when if you used RBD. There was some bugs and some problems. So this was way back before Hammer, I believe. So it started out with 13 OSD nodes, 146 OSDs, 500 terabytes of raw capacity, journals co-located with the OSDs on a 10 gigabit fiber network. All of it was basically installed by hand on each node. Some were bash scripts for deploying the configuration, but realistically it was a lot of work. And I was actually not in the original team that did that. One of the members is there if you want to talk about old war stories with them. So then came expansion. We proved that the cloud was useful. People were using it. We couldn't actually supply enough storage for everybody. So we were approved for an expansion of the cloud resources themselves, so the CPUs. And the approval came with money to really expand our storage into something that was much more useful. New tools had been developed since phase 1. So we expanded our cluster to 18 OSD nodes, 260 OSDs. We moved our journals onto SSDs, which helped a huge amount. Then we had 2.2 petabytes of raw storage. We're still using the same network. We still did our deployment kind of by hand, but we were starting to learn how to use Ansible at this point. So we devised a whole bunch of crafty, hand-bombed Ansible plays that worked really well, and when I came onto the team, which was right around this time, it was much easier to get our servers out. So, the cloud's useful, everybody's happy with it, we got more money. Everybody likes that, right? Research computing, hard to come by. So in 2018, we were granted more money for hardware, significantly expanded our cloud offering, and again, significantly expanding the research opportunities, the expansion of storage opportunity. We decided that instead of simply expanding the existing cluster, that we had enough new resources coming online, we would build a whole new cluster instead. This allowed us to bring up not only a brand new cloud and get rid of all of our cloud baggage we were carrying around, but also bring up a brand new Ceph cluster and greenfield the whole thing. So we deployed a new control plane. All the new hardware in the cluster was brand new. And what our plan was to get our users to migrate their data. We didn't do it for them. We set up some migration hosts, allowed them to rsync across, get their data out and into the new cloud. As they were freeing up our resources in the old cloud, we were deprecating those nodes and bringing them over and bringing them up into the new cluster. So then our new cluster is 32 OSDs nodes, 640 OSDs in total, 5.3 petabytes of raw storage, SSDs again for rocks and wall, and then we've got dual bonded 10 gigabit fiber. Our deployment was basically XCAT for host discovery and imaging, get it to the basic level. Then we have an in-house Ansible play that we use to bring it up for security practices, make sure it's hardened. And then we run Ceph Ansible on top of that for the deployment. We were allowed to clean slate. You don't get to do that very often. I've been doing this for a few years, and this is the first time that I've come into a project and I was allowed to actually start from fresh. We deployed Mimic. West was running Joule at the time. We changed over to BlueStore. Primary RBD pool is using an erasure-coded profile at 8.3. Very safe. I was told recently it's a manager's erasure code. Our images are all hosted on an erasure-coded profile as well. So we've also split the client and replication traffic over to 2 VLANs on the bonded network. So we've seen incredible performance increases as a result of a dead OSD or a dead node, where the clients actually don't notice any of that traffic on the rebuild. So finally, we've got the new cluster up and running. We want to look at it. We want to know what's going on. We knew from running it in the past that we weren't getting the full picture. So we've employed several layers for monitoring. We've got in-house systems statistics, UV stats we call it, University of Victoria, which runs against every node, gives us all of the hardware information, CPU usage, load, all of that stuff, disk utilization. Then we run Prometheus agents on all of the hosts. And then we run all of the alerts. All of the messaging goes through an internal management software we've built called Flare. It allows us to pipe all of our log messages from all of our applications straight into syslog-ng. Syslog-ng then aggregates down to a couple of hosts. It runs against a pattern matching database, which then allows us to set up triggers based on host type, on alert type, on everything, and alert the right people that can actually fix the problem. In the past, years ago, everybody on the data center services team would get an alert every time something happened. For dev, prod, or pre-prod now, we only get prod alerts out of hours, and it's only to the person that's actually watching the queue. Then we decided to go with visualization for Grafana. We use UV stats a little bit for our visualization, which is a plugin right into RRD. So you've seen similar graphs other people showing. So UV Stats does store all of our information for 7 years on every host in the entire environment. Allows us to go back in history and see what was going on. When we get an alert on our team, the first reaction isn't jump onto the host and start doing stuff. It's to go to the logs, go to the stats, find out what was happening,